Why is gravity absurdly weak compared to other forces? This mystery may point to hidden dimensions of spacetime. Gravity shapes galaxies and holds planets in orbit, yet it's the weakest fundamental force by an enormous margin. This is one of physics' deepest puzzles. Let's start with a shocking demonstration of how weak gravity really is. Imagine holding a paperclip with a tiny refrigerator magnet. That small magnet easily overcomes the gravitational pull of the entire Earth. The magnet's electromagnetic force defeats the gravitational attraction from 6 sextillion kilograms of Earth mass. This illustrates the hierarchy problem. Let's quantify exactly how weak gravity is compared to other fundamental forces. The gravitational force between two protons is about 10 to the minus 36 times weaker than their electromagnetic repulsion. That's a decimal point followed by 35 zeros. More precisely, the gravitational coupling constant is g times the proton mass squared divided by h bar c, approximately 10 to the minus 36. This enormous disparity is called the hierarchy problem. Why is gravity so incredibly feeble compared to the other forces of nature? Let's compare all four fundamental forces to see where gravity stands. Here's a visual comparison of force strengths at the atomic scale. The strong nuclear force is strongest, then electromagnetic, then weak nuclear. Gravity is so weak it barely appears on this scale. At atomic distances, we can assign relative strength values to each force. If we set the strong force to 1, electromagnetism is about 10 to the minus 2, the weak force is 10 to the minus 13. And gravity? It's 10 to the minus 39, an incomprehensibly small number that demands explanation. This raises a fundamental question. Why does nature exhibit such a dramatic hierarchy of force strengths? To understand gravity's weakness, we need to explore the Planck scale, where quantum mechanics meets gravity. Physicists use natural units built from fundamental constants to reveal the true scale where gravity becomes strong. The Planck mass is defined as the square root of h bar c over Newton's constant g. This equals about 1.22 times 10 to the 19 giga-electron-volts. This energy scale is enormous. The Large Hadron Collider reaches about 10 tera-electron-volts, a million times smaller than the Planck scale. This graph shows the enormous gap between the electroweak scale, where the Standard Model operates, at about 1 tera-electron-volt, and the Planck scale, where quantum gravity dominates. The hierarchy problem is essentially asking, why is there a factor of 10 to the 16th between these fundamental energy scales? One radical solution proposes that we live in a higher dimensional universe with hidden extra dimensions. What if our familiar three-dimensional space is actually embedded in a higher dimensional reality? Imagine our three-dimensional universe as a thin membrane or brain floating in a higher dimensional space called the bulk. The key insight is that gravity, unlike other forces, might propagate through these extra dimensions, while other forces are confined to our three-dimensional brain. The gravity we observe would be diluted by the volume of the extra dimensions. Our Newton's constant equals the true gravitational constant divided by the volume of extra dimensions. Gravity appears weak in our three dimensions because its strength is diluted as it spreads into the extra dimensions we cannot see. The brain world scenario provides a specific framework for understanding how extra dimensions work. This revolutionary idea was proposed by Arkani Hamed, Dimopoulos, and Dvali in 1998, now called the ADD model. In the brain world picture, Standard Model particles are confined to our three-dimensional brain, while gravitons can freely propagate into the extra-dimensional bulk. All Standard Model particles like electrons, quarks, and photons are stuck on our brain like ants walking on a wire. But gravitons, the hypothetical particles that carry gravitational force, can explore the full higher dimensional bulk. The relationship is, the Planck mass squared is proportional to the fundamental gravity scale m star to the power 2 plus n times r to the power n, where n is the number of extra dimensions and r is their size. How many extra dimensions might exist, and how large could they be? Let's explore different scenarios for the number of extra dimensions and their observable consequences. If there's one extra dimension, we can calculate the required size. With one extra dimension, it would need to be about 10 to the 13th centimeters, roughly the size of the solar system. This is ruled out by observations. 2 extra dimensions lead to a much more interesting possibility. With 2 extra dimensions, their size would be about 1 millimeter. This was experimentally testable and sparked searches for deviations from Newton's law at sub-millimeter scales. This graph shows how gravity might deviate from the standard inverse square law at small distances if extra dimensions exist. Experiments have searched for such deviations. With 3 or more extra dimensions, the required size becomes even smaller. For 3 or more extra dimensions, the size would be less than 10 to the minus 6 centimeters, making them even harder to detect directly. Lisa Randall and Raman Sundram proposed an alternative, warped extra dimensions. In 1999, Lisa Randall and Raman Sundram showed you could solve the hierarchy problem with just 1 warped extra dimension. Instead of flat extra dimensions, they proposed a single, strongly curved or warped 5th dimension. The metric has an exponential warp factor, e to the minus 2ky, where k is the curvature scale and y is the extra dimension coordinate. In warped geometry, the energy scale decreases exponentially as you move through the extra dimension. The Planck brane has enormous energies, while the TeV brane, where we live, has much lower energies. We would live on what's called the TeV brane, where all energy scales are exponentially warped down from the Planck scale. The TeV scale equals the Planck scale times e to the minus kr pi, where this exponential factor naturally generates the hierarchy. How can we test these exotic theories experimentally? First approach. Test Newton's law of gravity at very short distances to look for deviations. Torsion balance experiments use carefully suspended test masses to measure gravitational attraction at sub-millimeter scales. Current experiments have found no deviations from Newton's law down to about 50 micrometers, constraining large extra-dimension models. Second approach. Search for Kaluza-Klein graviton modes at particle colliders. Extra dimensions predict a tower of massive graviton states with masses m n equals n divided by r, where n labels the excitation mode. The Large Hadron Collider searches for events where gravitons escape into extra dimensions, appearing as missing energy in the detector. Third approach. Use astrophysical observations to constrain extra dimensions. Supernovae and neutron stars would cool faster if gravitons could escape into extra dimensions, providing powerful constraints. Let's connect this to quantum field theory and understand why gravity is special. A key question. In quantum field theory, why can't we renormalize quantum gravity like we do for other forces? Newton's constant g has dimensions of length squared, or equivalently energy to the minus 2 power. This makes gravity non-renormalizable. Unlike electromagnetism, where coupling gets weaker at higher energies, gravity's effective coupling grows stronger, making it non-renormalizable. The gravitational coupling at energy E scales as E squared over Planck mass squared. This grows without bound at high energies. This graph shows coupling strengths versus energy. Electromagnetic coupling decreases slightly with energy, while gravity's coupling grows, eventually requiring a quantum theory of gravity. Extra dimensions could lower the scale where quantum gravity becomes important, potentially making it testable at colliders. What if the fundamental gravity scale is actually at the weak scale, around 1 tera-electron-volt? The radical proposal is that the fundamental scale of gravity is actually around 1 tera-electron-volt, not the Planck scale. If the fundamental gravity scale m star is around 1 tera-electron-volt, quantum gravity effects become accessible to current experiments. This elegantly solves the hierarchy problem because there's no longer a vast gap between electroweak and gravitational scales. The observed Planck mass squared equals 1 tera-electron-volt to the power 2 plus n times r to the power n. Solving for 2 extra dimensions gives r approximately 1 millimeter, which was the sweet spot for experimental tests. What would we see at the Large Hadron Collider if this is correct? Most dramatically, microscopic black holes could be produced in particle collisions at tera-electron-volt energies. These black holes would have Schwarzschild radii around 10 to the minus 19 meters, incredibly tiny but potentially detectable through their decay products. We'd also see resonances from Kaluza-Klein excitations of the graviton at regularly spaced mass intervals. And we'd observe missing energy signatures from gravitons escaping into the extra-dimensional bulk. What have experiments found so far? Do extra dimensions exist? Despite extensive searches, the Large Hadron Collider has found no evidence for large extra dimensions or TeV-scale gravity. Large regions of parameter space have been excluded by LHC searches, but some possibilities remain allowed, particularly warped scenarios. Searches for graviton resonances have pushed limits on the fundamental scale. Current constraints require the fundamental gravity scale to be above 5 to 10 tera-electron-volts if large extra dimensions exist. This doesn't rule out extra dimensions entirely, but pushes the scale higher than originally hoped. Meanwhile, precision tests of gravity at short distances continue to improve, testing larger dimension sizes. Extra dimensions aren't the only proposed solution to the hierarchy problem. Supersymmetry proposes a symmetry between bosons and fermions that naturally stabilizes the weak scale. Supersymmetry operators Q transform bosons into fermions, and vice versa, with profound implications for the hierarchy. Technicolor theories propose a new strong force at the tera-electron-volt scale that dynamically generates the weak scale. Composite Higgs models suggest the Higgs boson is actually made of more fundamental constituents, explaining its relatively low mass. The anthropic principle argues that gravity must be weak in our universe, because only then can stars live long enough for life to evolve. Let's understand why gravity might behave fundamentally differently from other forces. Unlike other forces which couple to specific charges, gravity couples universally to all energy and momentum. The source of gravity is the energy-momentum tensor T mu nu, which describes the density and flux of energy and momentum. This universal coupling might be exactly why gravitons can explore extra dimensions, while charged particles cannot. Gauge fields like photons are confined to the brain by their coupling to brain-localized charges, while gravitons couple to all energy and can freely propagate into the bulk. Extra dimensions would have profound implications for cosmology and the early universe. In the early universe, at high temperatures, gravity would have been much stronger if extra dimensions exist. The Hubble parameter squared would scale as density squared over m star to the power 4 plus 2n, rather than the standard four-dimensional result. Modified gravity in the early universe affects the expansion rate during Big Bang nucleosynthesis, changing primordial element abundances. An exciting possibility is that dark matter could consist of the lightest Kaluza-Klein particle, stable due to momentum conservation in extra dimensions. Kaluza-Klein particles would interact through gravity and could constitute the dark matter halo surrounding galaxies. Let's dive deeper into the mathematical framework of extra dimensions. We begin with Einstein's equations in 5 dimensions, describing how geometry responds to energy. The 5-dimensional Einstein tensor GAB equals 8 pi times the 5-dimensional Newton constant G, 5 times the energy momentum tensor TAB. We then compactify the 5th dimension, typically on a circle with radius r, or an interval with boundaries. For a circle, the coordinate y is identified with y plus 2 pi r, implementing periodic boundary conditions. Any field can be decomposed into Fourier modes along the compact direction. A 5-dimensional field, phi of x and y, equals the sum over n of 4-dimensional modes, phi n of x, times e to the in y over r. From the 4-dimensional perspective, each Fourier mode appears as a particle with mass proportional to n divided by r. The zero mode, with n equals 0, is the massless 4-dimensional field we observe at low energies. Let's examine the Randall-Sundrum mechanism in more mathematical detail. The Randall-Sundrum scenario places 2 3-branes at the boundaries y equals 0 and y equals pi r. The metric includes a warp factor, e to the minus 2 sigma of y, multiplying the 4-dimensional Minkowski metric. For Randall-Sundrum, the warp factor is sigma equals k times absolute value of y, where k is the anti-de Sitter curvature scale. The 5-dimensional Einstein equations, with a negative cosmological constant, determine the curvature k. The curvature equals the square root of minus the 5-dimensional cosmological constant divided by 24 times the 5-dimensional Planck mass cubed. The Planck brane at y equals 0 has positive tension, while the TeV brane at y equals pi r has negative tension. The exponential warp factor, e to the minus k pi r, needs to be about 10 to the minus 16 to generate the observed hierarchy. This means K times R must be approximately 35, a moderately large but not extreme value. What are the concrete experimental predictions we can test? Extra dimensions predict specific modifications to Newton's inverse square law at short distances. The gravitational potential equals minus g mm over r times 1, plus the sum over n from 1 to infinity of r over r to the power n. We expect a tower of Kaluza-Klein graviton modes with masses proportional to n over r, where n labels the excitation mode. The mass of each mode, mn, equals n divided by r. Colliders could see missing energy signatures from gravitons escaping into the extra-dimensional bulk.